All right, so in this lesson, we're going to begin evaluating limits analytically. Now, it's essentially like think of it as like solving limits. Maybe when you first started, working with equations, you solved equations, but it's not exactly like solving, but you can kind of think of it like that if if that helps in solving limits, evaluating limits. Now, the reason we have to, be very strategic is because they're not intuitive. It's not like you can add, subtract, multiply, and divide the ways that we did in algebra. So we're going to be looking at some techniques and focusing on rationalizing and dividing out common factors as some of our main techniques. And then we're also going to look at some of the properties and make sure we apply them correctly. And then we're going to look at the squeeze theorem. Now, the first part of this lesson, we're going to go over properties. So it's going to be a little theoretical. We're not going to go too rigorous into it, but it is important that you at least get exposed to it, because you want to make sure you don't just get used to going about problems dealing with limits as if like none of their properties actually matter. Okay, so the most basic way that we want to go about evaluating limits is with direct substitution. So if we can find that the limit at some point x equals c exists, and you can plug in that value, maybe it's 3, maybe it's 5, then that's the best case. That's awesome. That makes your life a lot simpler. And this is basically known as direct substitution. So basically we can say that the limit as x approaches c of f of x is equal to f of c. That's again the ideal situation, because then it means that the function is continuous at c. It doesn't have any holes, doesn't have any gaps, doesn't do any weird like asymptotic like behavior. Now some of the basic properties and the limits that you'll see, kind of you can think of like a common sense limits. First one is the limit as x approaches c for some number. Now this is a constant. This is not a variable. So limit as x approaches c for b is just going to equal b, because you're not plugging any value into this. It's like basically you have an equation like y equals 5 or something. Like it doesn't matter what the x value is. Y is always 5. Now the second limit says that the limit as x approaches c of x is going to be equal to c. In this case, the expression is actually dependent on the x values, because it's a variable, but this is simply you're just going to plug in whatever that x value is for and you'll get, in this case, if you're going to plug in like c is 3, it'll be 3. Think of this as like a diagonal, like the line y equals x. And then the third one is when you have the limit as x approaches c for x to the n. So it's just like an exponential. And again, this is very simple, because you could just plug in that value. Like you can plug in the value, maybe it's x as x approaches 3, that's just going to be 3 to the n, whatever it is. So those are the 3 basic limits. Now let's look at some of the properties. Now again, don't worry about being too rigorous with this stuff, but it is important that you do gain some general understanding that you just can't go about limits however way you want. You have to be careful about when you're evaluating them. All right, the first one is called a scalar multiple, and that basically means that you can multiply a limit by some constant number, like it'd be 5. If it's like 5 times f of x, that's the same as finding the limit of f of x and then multiplying it by 5. So it doesn't matter if you do it before or after. Sum or difference, it's just like adding 2 functions. Like if you have like f of x was x squared and g of x was like 2x, you can add them, then take the limit, or you could take the limit, then add them. But we already defined that the limit as x approaches c for f of x is L, and for g of x will be K. So you can just add them or subtract them. Product, same idea. You can just multiply them. If you know what the limits are, you can just find those values and multiply them. And then a couple more basic ones. Quotient. You can divide the two functions as long as the denominator, in this case g of x, is not equal to 0. And the power, you can raise the function to some exponent, to some power. And again, it's just like as you think as x is like the third. The power is fixed. The power is not the variable. It's going to be fixed. It's going to stay the same throughout the problem. All right, now when we have polynomials, these actually are pretty easy to work with, because when you have a limit dealing with a polynomial, you can simply just apply direct substitution. Just plug in that value for c into the polynomial, and you'll get your limit. So if it was like, x cubed plus 5x squared, and the limit was x approaches 3, you can just plug in a 3 for the x. And I'm gonna go through several examples after a couple more properties, so don't worry. Next, when you're dividing them, when you have a rational function, let's say r of x is equal to p of x divided by q of x, then again, you can just simply plug in that value for x. If c was 5, you can plug in 5 for x and divide. Again, as long as the denominator function q of x in this case is not equal to 0. Just make sure you're not dividing by 0. Radicals work out nicely as well. When n is odd, it's going to be the nth root of x for the limit as x approaches c. Again, you just direct substitute that value in for x, and as long as the c value is positive, then you can take the even root, like the second, fourth, sixth, so forth. Now composite functions, it's going to look a little weird, and let's look at this carefully. In this case, we have the limit as x approaches c of g of x is defined to be L, and we're going to then have that value as our value that x is approaching. So we have the limit of f of x as x approaches L will be equal to f of L. So it's going to be a function of a function. Remember, a composite function is basically you're taking a value for one function and plugging it into the other one. And so it's going to look, like this. The limit of f of g of x as x approaches c will be equal to the f for the function of the limit of g of x as x approaches c. So do this part first, and that'll just be the same as that L, the f of L. Because that L, we see this interior right here is what we define up here. And here are just some of the trig ones. You can just simply apply direct substitution in for those ones as well. All right, now we're going to look at some of the theorem that we're actually going to use to start solving or start evaluating these limits. And this is going to be theorem, in this text looks at theorem 1.7. And this is going to apply when you have a function that is not defined at some point, at the limit point. Let's say if x is as x approaches c, let's say c is 3, but the function is not defined as 3. If you can find another function that's exactly like the original function, except that it has a defined value at that c, then they're going to be equal to each other. For that, their limits will be equal to each other. So this is what we're going to be applying a lot of the time when we can do direct substitution. And again, we're going to go through some examples in just a minute. So the general strategy that we're going to use is first, make sure you know and recognize what limits can be evaluated by direct substitution. That's the simplest case. It's quick, and you're going to make your life a lot easier. And that'll just be practice. And it's just applying those properties. It's just applying those properties that we just went through. Now, when this fails, so it's going to fail at some value c, we're going to apply theorem 1.7, which is basically saying again that we want to find a function that's just like the original function, except it's actually defined at that point c. And then we can make it equal to the original function, and then we can actually evaluate it and use it to solve the original limit for the original function. And this should say g of c actually, not just c. Let me fix that. Now, whenever you can, use a graph, to check your results. If if the function is reasonable enough to graph and look over. Okay, so now let's go through some practice ones. So these first couple ones are just going to be examples of limits where we can just apply those original properties, and they'll be quick and easy. So we have the limit of b as x approaches c. Remember, b is just a constant, so it's just like, let's say b could be like whatever, 3, 5, just some value. So the limit will just be equal to b. I don't know. I didn't mean to put a parentheses. The second one is an example of that other basic property. So limit of x as x approaches c, we can just plug in that c value for x, and then so it'll just be equal to c. The third limit is an example of the third property that we went over when we have an exponent. Remember that exponent is fixed, so we have the limit as x of x to the n as x approaches c. We can just simply plug in c for x, and we'll get c to the n as our limit. Okay, now problem D, this is an example of a polynomial. Remember, this 4x squared plus 3 is a polynomial, and this is just going to be the polynomial evaluated at x equals 2. So we just plug in 2 for x. So this will be just 4 times 2 squared plus 3. And so we'll get 4 times 4, 16, plus 3, and we'll get 19. All right, E, here's an example of a rational function. And we have the limit as x approaches 1. So if we plug in 1, we won't get 0 for the denominator. So we can simply just evaluate it by plugging in 1 into the top and bottom. So we have 1 squared plus 1 plus 2 over 1 plus 1. And so we'll get 4 over 2, and we'll get 2. For F, example of a radical, we can plug in 0 because if we evaluate, we have the square root of a positive number, and that's okay. So this will just be square root of 0 plus 4, or square root of 4, which will get 2 as well. And our last one, another radical where it's odd, but that's okay, because we can take the root of it. So we just plug in 3 for x, so we get the third root of 2 times 3 squared minus 10. So the third root of 2 times 9, 18 minus 10, the third root of 8. Remember, that would just be 2 because 2 to the third power, 2 times 2 times 2 is equal to 8. Okay, so now we're going to look at some more complex ones. We're going to have to actually do some stuff. Okay, so for H, we have the limit as x approaches 1 of x cubed minus 1 over x minus 1. Now here, if we were to plug in 1 for x, we would get 0 in the denominator. So this is undefined for x equals 1. So what we do is we just make another, we make another function just like this one, but where it's okay to plug in 1. And it's not just like, oh, let's just make up let's not just make up another equation. We do something to it to manipulate it. And what we can do is we can factor. This is actually going to be equal to, you can factor the top into x minus 1 times an x squared plus x plus 1. I mean, I don't really expect that you guys have to know off the top of your head, and you won't really have to worry about these types of ones popping up on your AP exam. I just know because I've been doing this for 100 years, but don't worry about being able to factor ones like this. You usually won't get ones this complicated. So anyways, so we factor this, and you can see you can cancel out the x minus 1 groups. And so then this ends up being x squared plus x plus 1. And it's this expression that becomes our g of x, or our other function. So our f of x is this. Like f of x, we define it to be the original expression as x cubed minus 1 over x minus 1. Now, the advantage is that we can plug in 1 into g of x. Because if you plug in 1 into g of x, you'll just get 1 plus 1. You can just get 3. So we can basically then take the limit as x approaches 1 of g of x. And that'll just be 1 plus 1 plus 1. 1 squared plus 1 plus 1, you'll get 3 as your limit. So the limit is actually 3 for this function and this function, for both functions. Now it's like, well, why? Like, what's going on? Why is that? Okay, so let's understand like why this occurs. So if we're going to graph g of x, we're going to have a parabola. And again, don't worry about calculating that. I already expect that you should be able to know how to do this. But if we were to figure it out, it's going to be a parabola that looks something like this. Let's call this g of x. I don't like the way this actually looks. Let me fix that. Okay, so if it's a parabola like this, looks something like this, and what this represents is the point on this graph 1, 3. Right? Because when x is 1, it's saying that the limit is 3, which is the y value, so the point 1, 3 on this graph. So what does f of x look like? Well, f of x, I find this pretty amazing, is that it's actually the exact same graph. It just has a hole at 1, 3. So if we were to graph it, you would just graph the exact same parabola, f of x, except at 1, 3, there's a hole. Call it, or it's a discontinuity. So it's essentially like it's kind of the way I like to explain to my students when they're working with this is like, how do you know when it's a hole? Well, think of it as just like you're removing something from it. So this graph, remember f of x, what we did is we removed this p. So think of it as f of x as you're removing that point when x is 1, or we remove the point when x is 1 on this graph. So it's exactly the same, except it just has a hole there. That's why we can apply this technique. So let's look at a couple other ones to gain a sense on, to gain a little more insight on what we do in other cases. Now, let's clear the road here. Here we have another case where if you plug in -3, we have the limit as x approaches -3. If you plug it into the denominator, you're going to get 0. So we can't do that. It's going to be, undefined for x equals -3. So what we're going to do is we're going to, do some math magic, and make it so that we can plug in -3 by changing this function. So we can actually factor this. Factor the top. This one should be pretty simple to remember. X plus 3 times x minus 2 over x plus 3. And there you can cancel out the x plus 3's. And so then this will be our g of x function. Our g of x will be equal to x minus 2. And so now we evaluate the limit of g of x. We find the limit as x approaches -3 of g of x. Remember, g of x will be this equation right here. It's basically just x equal to x minus 2. So if we plug -3 into x minus 2, we'll just get -5. -3 minus 2 will be -5. So then we can say, remember, because this is going to be our original function, so we'll define that as f of x. F of x will be equal to x squared plus x minus 6 over x plus 3. So these two graphs are going to, again, be exactly the same, except for at that point, -3. That's why we can say that the limit as x approaches -3 for f of x will be -5. So let's go ahead and write the limit as x approaches -3 of x squared. Well, let's actually just write f of x. Equal to -5. So that's our answer. Now again, let's actually just draw a sketch of this, because this is a fairly simple graph to know. We're just going to draw the graph of x minus 2. Let's draw them side by side. So for g of x, it's just a linear equation. Y-intercept, of -2 goes through 0, -2, 2, 0. And at that point, -3, not drawing the scale, the y value is -5. But our original expression for f of x, so remember we have f of x is equal to x squared plus x minus 6 over x plus 3. Even though this looks complicated, this is the exact same graph as this one, except it just has a hole at -3, -5. That's it. That's the only difference. And this, when I first, was learning this, this really blew my mind, because I just could not, grasp how this could just be a straight line just because we were able to do this math. But it's just, that's math for you. That's the exact same graph, except at -3, comma -5, there's a hole. Call that also a discontinuity. All right, so now let's look at the third case. Now, here we have the limit as x approaches 0. The square root of x plus 1 minus 1 all over x. If we plug in 0, we would get an undefined expression. So, we're going to have to, again, do something, Now, here we just can, factor because, you obviously just can't factor out something, x or 1 from here. So what we're going to actually do is multiply by the conjugate. Let me write that out, actually. So what this means is that we're going to have this expression. So let's go how should I write this? All right, let me do this actually. Square root of x plus 1 minus 1 over x. You're going to multiply this by the conjugate of this, or it's going to be just a weird version of 1, which is just going to be the square root of x plus 1. Instead of minus 1, you're going to have plus 1. And again, to make sure that you're multiplying by 1, you're going to have the denominator be the exact same, thing. I don't know why my pencil's doing this thing. Okay, so let's see if your math skills are up to par. So, just like what we do when we multiply, binomials, let's remember that when we multiply a square root by a square root, the square roots will just cancel. So if we multiply that by that, that simply becomes x plus 1. Multiply this square root by 1, you're going to have plus 1 times the square root of x, so plus square root of x plus 1. And then multiply the negative 1 by that square root. So you're going to have minus the square root of x plus 1. And then you're going to have that negative 1 multiplied by that 1. So you're going to have minus 1 at the end. Now, you be disciplined for the denominator because usually you won't have to do anything. So just leave it as is. Leave it as is, like an x times that whole group of x squared plus 1 plus 1. Not always, but when you get basic ones, you usually won't have to do anything. So what you can see is that this square root and this square root will cancel. They're just opposites. And what we have on top is just x plus 1 minus a 1. So what you have on top is just going to be an x. This may just go to the next line. So you're going to have x on top. And the bottom, you're going to have that x times the square root of x plus 1 plus 1. I usually put everything in parentheses when I'm doing stuff like this. I've learned that students can grasp the concept more easily. So I would actually put that in parentheses too. Anyways, you can see that these x's will then cancel. And so then all you have left is a 1 on top. So you have a 1 over the square root of x plus 1 plus 1. And this expression becomes your g of x. Now for here, you can take the limit as x approaches 0 for g of x because you're just going to have 1 over the square root of 1 plus 1. And so it's all good. So then, again, if we make this our f of x, assuming this is our f of x, So we can say the limit as x approaches 0 of f of x will be equal to 1 over the square root of 0 plus 1 plus 1. So 1 over the square root of 1 plus 1, so 1 over 2. And that's your answer. There we have it. Now, if you want to, look at this graph is actually a whole nother level. And I do not expect you to know it's off the top of your head, but I think I could probably fit a little sketch here. See if I can put a graph down here. So the original graph, so of f of x, is going to look something like this. This is f of x. Except it's going to have a hole at 0, 1/2. So it has a hole at 0, 1/2 because that's where we found the limit to be. G of x would be the exact same graph, except it doesn't have a hole at 0, 1/2. And if you have a graphing calculator, I would advise that you graph these so it'll really solidify your understanding, and it's gonna really make sure that you recall and remember this concept.